Okay, in this lesson, we're going to be looking at solving logarithmic equations. And most of this is stuff that we have already looked at briefly in section 3, but some of these problems do get to be a little bit more involved. So let's go ahead and look at this first problem here. I have an equation with a single logarithm. I need to know that when I see a problem like this with a single logarithm, I can write it as an exponential and probably end up an easier way to solve this. So 4 squared, base is 4, the 2 is the exponent, is going to equal 2x minus 6. So this is 16 equals 2x minus 6. You add 6 to both sides, 22 equals 2x, so x equals 11. One of the things that's different about the problems in this section compared to the last section is that we have to check our answers. Not all of the answers in this section are actually going to work. So I go back and put 11 in place of x in my original problem up here. So I'm going to have 2 times 11 minus 6 there in parentheses, and I'm checking to see, does all of that equal 2? So I have the log base 4, 22 minus 6 is 16, and that equals 2, right? 4 squared is 16, so that works. Okay, problem 2. Again, I have a single logarithm. The base is 5, and I'm going to write this as an exponential. So 5 squared equals x plus 3 cubed. Okay, this is 25 equals x plus 3 cubed. I'm going to take the cubed root of both sides. So I get x plus 3 to be the cubed root of 25, and then I subtract 3 from both sides. So I have the cubed root of 25 minus 3. Now that looks like a rather odd answer. If you want to put the negative 3 up front and then add the radical, you can do that as well. And we need to check our answer. So I go back to my original problem, and I'm going to put this whole thing in for x. So I have the cubed root of 25 minus 3. Now that's the x, and now I still need to add 3, and that is going to be cubed, and I am checking to see, does that equal 2? Well, what I have in these parentheses here with the minus 3 plus 3 is going to cancel. So I have the cubed root of 25, and that is cubed. I'm checking to see if that equals 2. Cubed root and cubes are inverses of each other, so they cancel out, and that just gives me 25. 5 squared is 25, so that works. Okay, problem 3. Again, I have a single logarithm. I'm going to write it as an exponential. So 3 squared equals x squared plus 8. 3 squared is 9. And once I get here, I'm going to subtract 8 from both sides. So I get x squared equals 1. So x equals positive and negative 1. And I need to check both of those to see if they're going to work. So I'm going to start off by checking the positive 1. Log base 3 of 1 squared plus 8. I'm going to check to see, does that equal 2? And this is going to give me the log base 3 of 9, and 3 squared is 9, so that works. Then I'm going to check the negative 1. So I have negative 1 squared plus 8, that's all in this bracket, and I'm checking to see does that equal 2. So I have the log base 3 of 9 equals 2. 3 squared is 9, so that works. So positive and negative 1 are my solutions. Okay, this problem is a little bit different, or quite a bit different, actually, to start off with, because I've got two logarithms on one side. So when we solved linear equations, one of the first things we did was to simplify each side before we started looking at inverse operations. And that's what I'm going to do here. I'm going to simplify this side of the equal sign by combining these two terms into a single logarithm. And it goes back to the properties of logarithms that we did in section 10.4. I have the sum of two logs. That means I can multiply these two arguments together to combine them into a single logarithm. And now that I have a single logarithm, I can write this as an exponential. 2 to the third power equals x times x minus 7. So this should be easy for y'all to solve by now. You get 0 equals x squared minus 7x minus 8. So setting each of these factors equal to 0 and solve, x is equal to 8 or negative 1. And then you have to go back and check both of these to see if they work. So checking the 8 first, I'm going to have the log base 2 of 8 plus the log base 2 of 8 minus 7, and I'm checking to see does that equal 3. Well, in this second term here, go back and correct that. Forgot to put my 8 in there. In the second term, I have 8 minus 7 is 1. Now I've got two logs that I can combine into one logarithm by multiplying the two numbers. 8 times 1 is 8, and this is 2 to the third power is 8, so that checks. And then looking at my second answer from over here, I have to go back and see if negative 1 works. So log base 2 of negative 1, actually I can stop right here. Since that is a negative, I know that that's not in the domain, that's not going to work. So my solution set is just 8. Okay, here is problem 5. It's just like problem 4. You're going to combine these into a single logarithm and then simplify the left-hand side, and then solve from there. So pause this and see if you can work this out on your own. Okay, there's your solution for problem 5. You can see that when I solve this equation over here, I ended up with 8 and negative 2, but when I went back to check, only answer that is going to work for me is 8. Okay, problem 6, we're going to simplify the left-hand side and then write our equation as an exponential and solve. Now, this problem is going to be different because when I combine these two, I'm going to end up with a quotient because I've got a subtraction here. I'm going to have to divide these two arguments. So now that I have a single logarithm, I can write this as an exponential. 4 squared equals x over x plus 1. So 16 equals x divided by x plus 1. This is the type of problem that you learned how to do in intermediate algebra. You need to multiply by common denominator to get that variable out of the denominator. So this is going to give me 16x plus 16. Over here on the left-hand side, on the right-hand side, that's going to cancel and give me x. So subtract 16x from both sides of the equation. 16 equals negative 15x. Divide both sides by negative 15. And that's going to cancel, so x is negative 16/15. And when you go back to check, there's really not a whole lot to it. You put this negative 16/15 back in place of that x, and you know already that it's not going to work because you can't have this value here being a negative number. So this problem has no solution. All right, problem 7 is just like problem 6. Why don't you try this and then come back and see if you got the right answer. Okay, there is your solution for problem 7. Your answer is 32/7, and that does check out. All right, let's scroll on down here to do a few more problems. Here I have log base 4 of 4 to the x power equals 9. Now this looks a little bit more complicated, but actually it's fairly easy. Remember that I can write this as an exponential. The base is 4. This number over here is the exponent, and this is the argument that's going to be over here on the right-hand side of the equation. So that's going to be 4 to the x power. So I can see here that x is 9. Problem 9, I have the natural log of e to the x equals 4. Remember, this is asking me, what power do I need to raise e to in order to get e to the x? I'll need to raise it to the x power. So x is just going to be 4. And again, I can think of this here as just a inverse function that cancels and gives me the x. So problem 10, I have the natural log e to the 0.005x power, and that's going to equal 2. And again, this is going to cancel out and just give me that exponent, 0.005x. And this is just a one-step equation. Divide both sides by that decimal. And so x is going to be 400. Problem 11, I have the natural log of e to the 0.002x power, and that's going to equal the square root of 5. Kind of an odd looking problem there. But on the left-hand side, I can simplify this because I have the natural log here is of base e, and this is base e, so this is just going to be 0.002x equals the square root of 5. And divide both sides of my equation by that decimal. So x equals the square root of 5 divided by 0.002. And I can stick that into the calculator, and I'm going to get approximately 1,118.03. It's important that you understand how to do problem 10 here because we're going to be using this again later on at the end of chapter 6. I'm sorry, the end of chapter 10, section 6.